Hello gentlemen, welcome to section 6.7 on acids, bases, and indicators. This is the first video of 4. Now, as we go into our talk on acids and bases, I first want to touch on definitions. Now, the definitions of acids and bases come from 3 different perspectives. The first perspective that we're going to be talking about is one that we've kind of already hit on, and that's with Arrhenius acids and bases. This comes from a guy named Savant Arrhenius. He said that acids make H plus ions in aqueous solution. So when you take an acid, you dissolve it in water, you have H plus ions present. And that H plus is kind of evident in our chemical formulas for acids. We know all of them start with hydrogens. And that's just a reminder that there are H plus ions in solution. An example of that is when hydrochloric acid, it's a gas, dissolves in water, and when you form that aqueous solution, you get H plus in aqueous solution and Cl minus in aqueous solution. That HCl dissociates into H plus and HCl. Now this H plus here, this is a very simplified terminology. In reality, so we use H plus because it is simple. In reality, the hydrogen ion H plus immediately attaches to a water molecule, creating something called hydronium. It's a hydronium ion, and its formula is H3O, 1+. So the example is here. As soon as this hydrochloric acid dissociates and you get H+, this H+ bonds with a water molecule. And the example is here. So H+ in aqueous solution bonds with a water molecule. Water is liquid, and it forms H3O, 1+, hydronium. So when we talk about H+, what we're really saying, and we're really talking about, and we're really referring to is hydronium. But to make it simple, we simply say H+. The complete equation is hydrochloric acid reacts with water, or basically is added to water, to form a solution of hydronium, H3O+, and your chloride ion. That's an Arrhenius acid. Now, an Arrhenius base is said to form OH minus ions in solution. It's here at the top. So when you put a base, which usually consists of a metal and a hydroxide ion, into solution, it dissociates into a metal cation and hydroxide, which has a 1- charge. An example of that would be NaOH, solid, dissolve it in water. You dissociate that NaOH into Na+ in aqueous solution and OH- in aqueous solution. Now, over time, scientists extended their definitions of acids and bases beyond Arrhenius' definitions of acids and bases. That brings us to our second definition. It's called a Bronsted-Lowry acid and base definition. This comes from 2 scientists, one named Johannes Bronsted and Thomas Lowry. Put that together, you have the Bronsted-Lowry theory of acids and bases. They said that acids are H+ ions, or proton donors. They said that bases are H+ or proton acceptors. You might be saying, well, wait, protons? What do you mean protons? We're talking about hydrogen here. You're right, we are. Now, H+, let's take a closer look at what that means. So acids, H+ donors, bases are H+ acceptors. Now let's look at hydrogen. An atom of hydrogen has a central nucleus here, represented by this small circle. In my nucleus, I have protons and neutrons, and around it I have my electrons, of course. Hydrogen has an atomic number of 1, so it has 1 proton. With that atomic number of 1 and a mass of 1, it has no neutrons. Around this nucleus, I have 1 electron that hydrogen has. This is just electrically neutral elemental hydrogen, an atom of hydrogen. Now, when this hydrogen reacts, in the case of, let's say, hydrochloric acid, this hydrogen has its valence electron taken by a chlorine atom. This hydrogen then forms H+, this chlorine forms Cl-, and they stick together through electrostatic interaction or attraction, and then they don't dissociate until they're put in water. Now, this H+, let's talk about how that's formed. So, once this electron is given to this chlorine, we can think about this electron cloud being taken away because there's only 1 electron there. Once this 1 electron leaves, we get this, a nucleus that simply holds one proton and no neutrons. So essentially all this is a proton, and this is a hydrogen ion known as H+. So H+ essentially, is just a proton. That's why in our definition of Bronsted-Lowry acids and bases, we call the H+'s protons that are being donated or accepted. Our third definition is called a Lewis acid or a Lewis base. This comes from a scientist called Gilbert Lewis. Is this the same Lewis of Lewis structures? Yes, it is. So acids. Lewis says that an acid is an electron pair, or we know them as lone pair, acceptors. Acids are electron pair acceptors. And bases are electron pair donors. Now this makes more sense when we look at Lewis structures, hence the name Gilbert Lewis. Now an example of this would be when H+ reacts with water to form hydronium. We saw this reaction on the first board when we talked about it not just being H+, but it really being H3O+, hydronium. Now let's look at this in Lewis structure form. So I have H+, and it's bonding with or being reacted or added to water. Now water has two lone pairs here. These lone pairs are going to reach out and grab this H+. And when they do, you can think of it as them donating their lone pair electrons to this H+. Since these are donating their lone pair electrons, or unbonded electrons, we know that it is a Lewis base. Since this hydrogen ion is accepting these lone pair electrons, it is our Lewis acid. And when that happens, we get hydronium. We have our Lewis acid and our Lewis base reacting together to form hydronium. Another example is here. We have sulfur trioxide reacting with water, forming sulfuric acid. Now, here we have this Lewis structure here. It's a sulfur attached to 3 oxygens, double bonded each site. These oxygens here are already satisfied. Sulfur is oversatisfied, but it can do that. It can expand its octet. It reacts with water. Water has lone pair electrons here. These lone pair electrons are going to attack this sulfur to bond on and expand sulfur's octet even more. Since these electrons are being donated, this is my Lewis base. Since this sulfur trioxide is accepting the lone pair electrons, this is my Lewis acid. When that happens, they form sulfuric acid, which has that chemical formula. The take-home message is this. Know that Lewis acids accept electron pairs. And that Lewis bases donate electron pairs. If you don't understand the arrows and the different mechanisms here, that's okay. But know this part here. Lewis acids will accept electrons, Lewis bases will donate. The last bit of information you should know, just in general about all acids and bases that pertain to all 3 definitions that we've gone through, is this. Acids react with metal, they have a sour taste, and they're really good conductors, meaning they're great electrolytes. Bases, they don't react with metals, they have a very bitter taste, they're slippery in their feel, like soap, and they're also very good conductors. So I'm going to take notes on this and look forward to your second video.